In the next 10 seconds, your body will absorb more energy from the sun than your smartphone uses in a day. Multiply that by the surface of the Earth, and we're talking about 173,000 terawatts of solar power continuously striking the planet. That's over 10,000 times the total energy consumption of all humanity. So the question is not whether there's enough solar energy, the question is, how efficiently can we catch it? Solar panel technology, or photovoltaic technology, is our best answer so far. And while most of us picture flat blue panels on rooftops, the science behind them is a lot deeper, literally quantum deep. At the core of every solar panel is a thin slice of semiconducting material, most often silicon. Not because it's perfect, but because it's abundant, stable, and easy to purify. When sunlight, composed of photons, hits the silicon, something remarkable happens. The energy of the photon can knock an electron loose from its atom. Now, a single silicon solar cell only converts about 15 to 22% of the sunlight it receives into usable electricity. Why not 100%? It's because photons come in different energies, and silicon only responds efficiently to a narrow band of that spectrum. Photons with too little energy pass right through, and those with too much simply lose their excess energy as heat. To harness that liberated electron, solar cells are built with an electric field. They use two layers of silicon, one doped with phosphorus to have extra electrons, N-type, and one doped with boron to have electron holes, P-type. Metal contacts on the top and bottom of the cell collect that current and send it through wires, giving you electricity that can power your home, your devices, even spacecraft. But the story of solar panels doesn't stop at rooftop arrays. Let's talk about efficiency. Traditional single-junction silicon cells have a theoretical efficiency limit of about 33.7%, known as the Shockley-Kayser limit. That's because of the physics of the material and how it interacts with sunlight. To go beyond that, researchers have developed multi-junction solar cells, stacking different materials that capture different parts of the light spectrum. Some of these can reach efficiencies above 40%, and in laboratory conditions, even past 47%. Of course, these high-efficiency cells aren't cheap. They're typically used in specialized environments like satellites, Mars rovers, and solar-powered aircraft, where cost is secondary to performance. Back on Earth, innovation continues with materials like perovskites, synthetic crystals that promise high efficiency at low cost, with easier manufacturing than silicon. In just over a decade, perovskite cells have surged in efficiency from under 4% to over 25%. However, they come with challenges, including long-term stability and the use of toxic lead, though new research is actively tackling both. Engineers are now exploring bifacial panels that capture sunlight from both sides, building integrated photovoltaics where the solar tech is embedded into windows or facades, and even transparent solar cells that could turn your phone screen into a power source. Globally, solar energy is now the cheapest form of new electricity generation in history. In many regions, it's beating coal, oil, and gas purely on economics, no subsidies required. Yet, solar still accounts for only about 4 to 5% of total global electricity production. The gap between what we can do and what we are doing is still enormous. But here's the twist. Even if we covered every rooftop and every sunny field with high-efficiency solar panels, we'd still face a core challenge: energy storage. The sun doesn't shine at night, and weather is unpredictable. So the true future of solar power isn't just in better panels, it's in the systems that let us store and use that energy exactly when we need it. Lithium-ion batteries, flow batteries, hydrogen fuel systems, even gravity-based storage, all of these are pieces of the puzzle. Because collecting energy is only half the battle. Storing it, and distributing it intelligently, is the next frontier. We're not just building solar panels. We're building a new kind of civilization, one that decouples prosperity from pollution, where power flows from the sky, silently and endlessly. That's power. That's potential. And it's already being harvested, atom by atom, electron by electron. If this made you see solar power in a whole new light, share it.